Hey everyone, and welcome. Today we're going to dive into a hidden force that's shaping literally everything around us. We're talking from the dirt under our feet to the actual cells inside our bodies. It's the secret reason why the real world almost never behaves the way it's supposed to in a nice, clean lab.
So let's start with a big question, kind of the central puzzle of this whole thing. Why do our best, most carefully controlled lab experiments so often fail to predict what actually happens out in messy, unpredictable reality? It's a real head-scratcher, and scientists have been wrestling with it for a long, long time.
And here's why that puzzle is so tough. Just look at the difference. On one hand, you've got the lab. Everything's perfectly mixed, the concentrations are uniform, the reactions are predictable. It's a pristine, controlled world. But the real world, that is the complete opposite. It's messy, it's uneven, it's all over the place. And that one fundamental difference, well, it changes absolutely everything.
Now, you might think the answer is some super long list of complicated exceptions, but it's not. The answer is actually a single, really elegant principle that's at play on every scale you can possibly imagine. Okay, so that brings us to our first big idea, where we're going to unpack this core concept. We're talking about the principle, a simple difference that is literally the engine for change. And this principle, it's called a concentration gradient. And the definition is it's beautifully simple. It's nothing more than the difference in the concentration of something between two places. That's literally all it is. One spot has more of a substance, the other spot has less. Probably the easiest way to get your head around this is to just picture a hill. The difference in height between the top and the bottom, that's what creates the slope, right? Well, the steeper that hill, the bigger the difference, the faster a ball is going to roll down it. That slope, that is the gradient. And I bet you remember a classic example of this from biology class. Osmosis. It's just water molecules moving from a place where there's a ton of them to a place where there are fewer. So what's the engine making that happen? You guessed it. It's the concentration gradient. So here it is, the big aha moment. The really crucial point is that the difference itself is the force. The imbalance, the inequality, the steepness of that hill, that's what makes things happen. It's what turns a static, boring situation into a dynamic one. Okay, so we've got the basic principle down. Now let's see how this thing gets absolutely supercharged in the real world. In this next section, we'll look at how nature uses it as a kind of hidden engine for chemical reactions. Think about it. Out in the real world, nature is constantly creating these gradients. A rainstorm washes chemicals into one spot in the soil, a river's water level changes, a plant root releases a burst of nutrients. These create what scientists call reactive pulses, basically these little localized hotspots of high concentration that are the exact opposite of uniform. So that's the key question, right? We know these concentration hills are everywhere, but how do they actually interfere with chemistry? How do they change the speed of reactions? And this is where the science gets really, really cool. It turns out it all depends on a property of the reaction called its order, which we're calling B here. If that B value is less than 1, the gradient acts like a turbocharger. It enhances the reaction, speeds it up. But if B is greater than 1, it slams on the brakes, inhibiting it. And in some extreme cases, if B is over 3, the brakes get hit so hard the reaction pretty much grinds to a halt. Now, this chart, it might look a little intense at first, but just think of it as a master map of this whole effect. It's like a cheat sheet for real-world chemistry. If a reaction's order value, that's on the bottom axis, is low, it lands in that blue zone on the left. That's the accelerator. But if the order is high, it shifts over into the yellow zone on the right. That's where the gradient slams on the brakes. It's basically a universal rulebook for how things really work outside the lab. Let's make this concrete with a real-world example. The oxidation of pyrite, you probably know it as fool's gold, it has a reaction order of 0.5. So, looking at our map, where does that fall? Deep in the blue accelerator zone. And the result is staggering. In a natural setting with all its gradients, pyrite can oxidize up to 10 times faster than a perfectly mixed lab experiment would ever lead you to believe. That's the power we're talking about. All right, so this isn't just some abstract thing happening out there with rocks and soil. Let's bring this home. We're going to move from the outside world to the one that's inside every single one of us and check out the personal connection. Believe it or not, a life or death concentration gradient is hard at work inside your own kidneys right now as you're listening to this. This principle isn't just for geology, it's absolutely fundamental to your own body. So how does this work? Well, your kidney is a master architect of gradients. What it does is it actively pumps a bunch of salt into a specific area called the medulla, and that creates this really steep salt hill. That gradient then becomes this incredibly powerful driving force. As fluid filters through the kidney, that super salty environment naturally pulls water out through osmosis. It's a brilliant system for letting your body conserve water and make concentrated urine. And look, don't just take my word for how important this is. Medical sources are crystal clear on this. This gradient isn't just helpful, it is essential. Without it, your body's entire water balancing act just falls apart. So the bottom line is, if that gradient fails, your body it loses its ability to hang on to water. And that's not a small problem. It can lead to severe dehydration and a whole cascade of really dangerous health issues.
So, after all that, what's the one big lesson we should take away from all this? Let's bring it all together in our final takeaway. The world is simply not well mixed.
This image just says it all, doesn't it? It doesn't matter if you're looking at a huge landscape on the kilometer scale or you're zoomed way in to the millimeter scale inside a beaker. Tiny, unresolved gradients are everywhere, and they are constantly altering reality, making it different from our simplified models. When you boil it all down, gradients are that universal engine of change. They're the difference that takes a quiet, predictable, well-mixed world and turns it into the dynamic, chaotic, and fascinating one we actually live in. So I'll leave you with this thought. Now that you know what to look for, now that you can sort of see these invisible hills and slopes all around you, where else are gradients shaping your world? Thanks for joining me.